Hi, and welcome back to a video series on MAT 1033 Intermediate Algebra. This is video number 24 in the series, Properties of Graphs of Functions. We're going to focus on graphs of functions, excluding relations in this video, and some of their properties and features. In this course, you can presume that a graph of a function is going to be a curve of some kind. Now, we're going to look at three features in this video. We're going to look at when are graphs increasing, decreasing, and constant. Where do they achieve their maximum and minimum values? And when do they display what's called asymptotic behavior? And we'll discuss that. Now, because functions only have one y value for each x value, we can actually give a meaningful single answer to this question. As x gets bigger, does f of x also get bigger? Does it get smaller, or does it stay the same? So here's an example of a function. As x gets bigger, we mean x going from left to right. So going from left to right, my function here is getting bigger. So I've shaded this part of the x-axis in green. It stops that kind of behavior here and starts getting smaller. So I've shaded that in red. Here it stops again, holds level. So I've shaded that blue. And then it starts increasing again. So I've shaded that green again. What we can do is we can break down that behavior in the following way. That f of x is increasing on the interval from negative infinity up to a and from c to infinity. It's decreasing from a to b, and it's constant from b to c. Here, these are not coordinates. They are intervals representing these intervals on the x-axis. Notice that we didn't include the endpoints. Why? Well, at the endpoints, at a, for example, it's neither increasing nor decreasing. It's changing from increasing to decreasing. That's a different kind of behavior. That's actually called a critical point. You'll learn about that more later. So here I have some critical notes. I want you to copy this to prove you watched the video. It's just basically an analysis of that definition. As x goes from left to right, if you see f of x going up, it's increasing. If you see it going down, that's decreasing. And if you see it holding constant, that is what we call constant behavior. So now where f of x stops increasing and starts decreasing, right, this point, this xy point here is called its local maximum. We'd say its y value is its maximum value, or we'd say at this x value, that's where it has a maximum. They look like little hills like this, or sometimes they look like little upward pointing cusps. Where it has the opposite kind of behavior, where it stops going down and starts going up, that's where it'll have its minimum value. We call these local maxes and mins because maybe the function does something else over here, but as far as nearby points are concerned, this guy's the smallest. And they either look like little valleys or these little downward pointing cusps. These are the two most common kinds of local minimum. Now, if these are how it behaves locally, how does it behave overall? What are the overall biggest and smallest points? Well, that's what we call absolute maxima and minima. Now, if there are absolute maxes and mins, they occur at either the local maxes and mins or at an endpoint of the function. So where the curve of the function starts and stops. But they don't have to have either. Like, think about a line. A line goes up forever and down forever. So it doesn't really have a highest and lowest value. It has no absolute max and min because infinity and negative infinity aren't numbers. Moreover, it has no bumps, no valleys, nothing like that. So it has no local maxes and mins either, right? So it has no absolute and no local maxes and mins. Lines are pretty boring from this question's perspective. Here's one that's a little less boring. Let me get this in frame, right? So this function starts here, it goes up, it goes down, it goes up, it goes down. Where are its local maxes and mins? What is its absolute max and min? So here I've drawn some dashed lines to kind of show the y values. At a, it starts increasing, stops increasing here and starts going down. So this is a local maximum at bg. Likewise, we have one of those here at df. There's a local minimum where it stops going from decreasing to increasing at ci. And then there's an absolute maximum. So this is its overall biggest point. This is the highest y value on the graph. So df is the absolute max. Notice that an end point might also be an absolute max or min. Here, this is a absolute minimum value. There are no values on the graph with y values smaller than j. So aj is the absolute minimum. And the difference between maxima and maximum, right? Maxima is the plural and maximum is the singular. So here's some more critical notes. I want you to copy this. This is what local maxes look like. They go from increasing to decreasing. This is what local minima look like. They go from decreasing to increasing. An absolute max or min is either going to be a local max or min, or it could possibly be the endpoint. If it has no endpoints, then either it's a local max or min, or maybe it goes off to infinity and then it has no max, or goes down to negative infinity and then it has no min, right? So those are things to consider when you are addressing questions about maxes and mins. Another important kind of behavior is called asymptotic behavior. So asymptotic behavior is when the curve of the function gets closer and closer to some line. Without ever really sticking to and becoming that line, it just gets really, really close to it, arbitrarily close as the curve proceeds. There's two main flavors of this. One is called a vertical asymptote, where it gets closer and closer to a vertical line. And here they could both go off in one direction, or they could split in this way. And then there's horizontal asymptotes, where it seems to get closer and closer to a horizontal line. Now, some things to note. Number one, vertical asymptotes can't be crossed. If they crossed and then came back to get closer the way this one kind of does, then that wouldn't be a function. It would fail the vertical line test. Vertical asymptotes are generally not defined. We leave this x value out of the domain. That's an important point. We'll talk a lot more about that later, but for right now, you should just remember that where it shoots off towards positive and negative infinity like this, it generally doesn't have a defined value. And so that point can't be in the domain because all points in the domain must be assigned a value. Now, there could be as many vertical asymptotes as you like, 0, 1, 2, 2 million. There could be an infinite number of them even. But horizontal asymptotes, there can only be 2 of them. Because really what we're talking about is that as x gets arbitrarily large or arbitrarily small, negative large, right, it gets closer and closer to some line. It has to pick a line in order to get closer and closer to, and it only has these 2 directions to work with, so there's only 2 possible horizontal asymptotes. So y asymptotes cannot be crossed, and they're not defined at that point. That point is not in the domain. Horizontal asymptotes can be crossed, but there's only 2 of them, while there might be an arbitrary number, perhaps even an infinite number for some functions of vertical asymptotes. There's even slanty boys that have this kind of oblique line to them, right? These call these slant or oblique asymptotes. They follow a slanted line. We're not going to talk about them so much, but notice that it kind of has the same behavior. This red curve is getting closer and closer to this kind of slanted line, and then on this side also closer and closer to this slanted line. Even though it's got a little bump in the middle, it eventually becomes very much like that line. Now, regardless of which kind of asymptote we're talking about, we want to give an equation for that line that it's getting closer and closer to. Let's talk this through with an example. Let's talk about this. This is one of my favorite functions, the reciprocal function 1 over x. First of all, let's note that we cannot plug in 0 into this thing, so the domain excludes 0. This kind of 0 parens union parens 0 notation, that's how you pull a point out of the domain and say, okay, but not there. Right? Okay, but not 0. When x gets really tiny, the reciprocal of something tiny and positive is a huge positive number. The reciprocal of something negative and tiny is a huge negative number. So it shoots off towards infinity this way and shoots off towards negative infinity this way. It hugs the y-axis, which is the line x equals 0. Notice that no matter how big a number you put in here, you'll never be able to have 1 over that number be 0. 1 over a positive value is small, but never 0. Same thing with 1 over a negative value. It's a small negative number, but never 0. And so 0 is omitted from the range as well. Likewise, for the same reason, this is getting closer and closer to the x-axis without going over it. That is the line y equals 0. So here's more critical notes. I want you to, again, write this, copy this, show me later for credit. This is, roughly speaking, the behavior of horizontal and vertical asymptotes. They look like they get closer and closer to horizontal and vertical lines, respectively. All right, now I would like you to do some praxis. Let's practice for the day. Here is a function. I want you to state its domain and range. Where is it increasing, decreasing, or constant? What are its local maxes and mins? What's its absolute and maximum and minima? And what are there any horizontal and vertical asymptotes? Pause the video and see if you can figure out each of these 5 questions. Okay, let's see how you did. To start with, what is the domain and range? So remember, that's the used x values. We generally omit points that correspond to vertical asymptotes, and this is one for sure. And over here, the last point that it gets to is C and includes C, because this is a dark circle. So we have this blue set, which we can encode in interval notation this way. So everything down to negative infinity up to b, and then not including b, which we omit like this, b parens union parens b, that says up to b but not including it, after b but not including it, up to c and then including c. What about the range? Because there's this vertical asymptote behavior here, it hits all these values going down as far as you can go. So the lowest value it gets to is negative infinity, not inclusive, to show that it keeps on going down. Then it goes up to D, attains D, and stops right there. So that's why we put a bracket here and shows that it gets no higher than D. Okay, so now let's talk about number 2. Number 2 is, where is this increasing or decreasing or constant? Let's start with the easy one. It's not constant anywhere, right? So there's nowhere on this graph where it ever holds steady for any flat line. It's decreasing. Well, here it starts, remember, we're going to do this as x goes to the right. So we want to keep following this to the right. Even though it's a little flat here, as we go to the right, it starts going down. So this is all decreasing until it reaches its lowest point. It turns from red to green here. And then from A up to the origin, up to 0, it gets bigger and bigger. Its y value is d here, but the value at the origin for x that we're going to be interested in making our interval in terms of is 0. So it's then increasing up to 0, then decreasing from 0 all the way to this asymptote, which occurs at the x value of b. And then after that, it gets bigger again. Now, don't get too confused by this downward facing arrow. Again, we're going as x goes to the right. What is our function doing? Our function is getting bigger and bigger, so it's increasing on this interval. So to summarize, it's increasing from a to 0, that's here, and from b to c, that's here. And it's decreasing from negative infinity up to a, that's this branch here, and from 0 up to b, that's here. And it's nowhere constant. Where are its local maxes and mins? Well, there's one. There's another. It's decreasing, and then it starts increasing. So this is a local minima. It's increasing, and then it stops doing that and starts decreasing. So this must be its local maxima. So these are our 2 local maxes and mins. We have one at 0D for the max, A, E for the min, and then what about this guy? So we could check this endpoint here. There's only one endpoint to check, and it goes with G. That's not a highest or lowest value. Right here, we can see the low values are kind of swallowed up because this thing is going down towards negative infinity. So there is no lowest value, right? It goes down to negative infinity. It gets more negative than any negative number. So it has no lower bound. It has no absolute minima, but it does have an absolute max. And that corresponds to this local max, where it reaches its highest possible value at 0D. What about horizontal and vertical asymptotes? Well, you probably guessed those. That's this dotted line, right? Where, maybe nothing happens over here, but all we need is for it to look like it's hugging this line indefinitely over on this side. That's a horizontal asymptote. And these two are shooting off in the same direction. That's okay. They're hugging this line. The horizontal line gets a y equals f, where f is not a function. It's some value here that I picked out. And this is x equals b, or where b is this x-axis value right here. All right, that's it for this video. Thank you very much for your patience. Have a nice day and good luck with your studies. I'll see you in the next video.